Welcome back everyone. In the last lecture, we had seen what are the practical problems with PID controllers, and we also saw in a demo how to solve that. I had told at the end of the lecture that would be the end of classical control part for this course. From today, we would be starting the modern control part of the course. So, let us recap one of the slides that I had shown you at the beginning of these lectures. If you remember, I had told earlier that the mathematical model of a system can be seen from an internal view or from an external view. We had seen the external view till now, where basically we were writing down the system's differential equations and converting them into transfer functions. This approach is what is known as the classical approach or the frequency domain approach of modeling. Now, this was an intuitive framework because Bode plots and root locus gave us an intuitive understanding about the system behavior. We also saw that intuitively we could say when should we use an integral controller, when we should use a derivative controller or a PID controller as a whole. All these worked on the intuition. We saw the output of the system and then we applied our intuition and came up with a solution for the control problem that we had. However, there are limitations to this approach. The limitation is that transfer functions are generally restricted to linear time invariant systems, and for if you want to apply for nonlinear case, then you will have to do certain approximations and then only use transfer functions. Further, this approach is limited to single input single output systems. Although you can come up with transfer matrices for multi input multi output systems, but dealing with transfer matrices is not that intuitive. So, this is another limitation of sorts of transfer function approach. Next, we move to the internal view approach. So, the internal view reveals a system's inner workings. Basically, we not only just look at the input and the output variables of the system, we also consider certain internal variables of the system called state variables. And in this approach, like in the external approach, we had transfer functions. In this approach, we will have something called state space representation. These are first order differential equation using matrices. Good thing about this approach is that it is easily extendable to MIMO systems, multi input multi output systems, and this approach can also be extended to nonlinear and time varying systems. So, there is a lot of flexibility in this approach. Now, the state space approach operates directly in the time domain, like the transfer function used to operate directly in the frequency domain, because S was frequency, if you remember, complex frequency. State space representation operates in the time domain. So, in some sense it is a time domain approach as well. And since we will be dealing with matrices and vectors in this approach is numerically implementable. By numerically implementable, I mean that software packages can easily handle this type of modeling because there are matrices and vectors involved here. So, from computational perspective also this approach is better. So, now let us dive in to what exactly is this internal view or what exactly is this state space approach. For that we will first define something called system variables. Remember, state space approach is written in terms of something called state variables. Now, in order to understand state variables, first you have to understand what are system variables. Now, the definition goes that any variable that responds to an input or initial condition in the system is called a system variable. Okay. So, for example, if you take this RLC circuit, in this circuit this current through the resistor, this current through the inductor, current through this capacitor C1, current through the capacitor C2, the voltage across all these variables will be considered as system variables, and here Vt is your input. So, Vt is not a system variable, Vt is something called forcing variable, which we will soon see. So, these variables are influenced by these inputs, and not only that, these variables are also influenced by the initial conditions that are present for these inductors and capacitors. So, that is why these are called system variables. So, this is a collection of all the variables that responds to any change in input or initial condition. Similarly, for a spring mass damper system, your position xt. So, suppose you are applying a force here, this is the forcing variable. Here xt is your position, x dot is velocity and x double dot is your acceleration, and those becomes your system variables in this case. What are forcing variables or forcing functions? The external variables that acts upon the system, so that these system variables changes are called forcing functions or forcing variables. In other words, these acts as input, these are in your hands, you can change this. When you change this, the system variables gets affected. So, in these two examples, the forcing variable is voltage in the RLC circuit and the forcing variable is force in the mass spring damper system. Now, there is this idea of linear combination. What is linear combination? So, we know what system variables are. Now, if you take, suppose you take two system variables and then you add them up, then we say that it is a linear combination. You can scale the variables up and then add them, then we will call it to be a linear combination. So, linear combination, the formal definition is a linear combination of n variables xi, okay, where I is from 1 to n, is given by the following sum. Okay. Here alpha n minus 1, all these are numbers. So, for example, if you remember in the previous example that I showed, so these two were system variables. So, I can say that 2 times of IL plus 3 times of IC1 is a linear combination of the system variables, these two system variables. Okay. Now, see, this might not have any physical meaning also. For example, Vc1 is the voltage across capacitor C1, right, and IL is the current through the inductor in the previous example. So, I can say that 2 times of this plus 5 times of this is a linear combination of Vc1 and IL. These terms, physically this term 2 times Vc1 plus 5 times IL has no meaning, because one term is voltage and the other term is current. So, even if you add them up, this has no physical meaning, but mathematically we can do that. Okay. So, this has mathematical meaning, but no physical meaning. Okay, this is a very important thing to understand, that certain things might not have any physical meaning, some mathematical terms might not have physical meaning, but that mathematical terms will help you to get to some results that will have physical meaning. You will see that it helps us in many ways. Okay. So, now if we will talk about something called linear independence. Now, suppose you have two variables or more than two variables. Now, the set of variables is said to be linearly independent if none of the variables can be written as linear combination of the other. Okay. I will explain it with the help of an example. So, let us say we have this RLC circuit. Now, we had already seen these are the system variables. Now, notice that in this RLC circuit, IL is equal to I1 plus I2, right, because the current through this inductor, this current is nothing but I1 plus I2. So, then you see, if I know the information of I1 and I2, I will know the information of IL. So, in this case I will say that these three variables IL, I1 and I2 are not linearly independent. They are linearly dependent because IL can be written as linear combination of I1 and I2. Similarly, IL here is equal to IR1. So, then we will say that IL and IR1 together, this set IL and IR1, this set is linearly dependent. Okay. Now, what can be linearly independent? So, here IL or I1 and I2, these two currents are linearly independent. Okay. Because I cannot write I1 in terms of I2 or I2 in terms of I1. Okay. So, then this becomes a linearly independent set. As a matter of fact, here IL capacitor voltage Vc1 and the voltage across the capacitor C2. So, this voltage, this is Vc2, this voltage, and this is Vc1, this voltage and the current through the inductor are also independent actually. Okay. So, this you cannot write these three terms in terms of each other. You cannot write capacitor voltage in terms of inductor current and the other capacitor voltage. Now, why are we talking about linear combinations and linear independence? You see, we first talked about system variables, from there we talked about independence of variables, okay, and then we talked about linear independence. First we talked about linear combination and then we talked about linear independence of variables. Why are we talking about that? We are talking about that so that we can define what state variables are. Remember, we started this topic with the idea that we want to talk about state space modeling. So, in order to understand state space modeling, we have to first understand what is a state variable. System variable we understood, all collection of all variables, collection of all the variables in a system which gets affected by input and initial condition. Now, among all these variables, there is a set of linearly independent variables. Okay, again, what is linear independence? You cannot write these variables in terms of each other as linear combinations of each other. So, among this big set of system variables, there is a small set of linearly independent system variables using which you can write about all the other system variables in the of the system. Basically, if you know the information about this small set of system variables, you will be able to write down the information or the values or the functions of the other system variables on the system. So, if you have to write down the definition of state variables are the smallest set of linearly independent system variables such that the values of the members of the set at time t naught along with known forcing functions completely determine the values of the system variables for all t greater than equal to t naught. Quite a mouthful, but the idea is very simple. Suppose you have, let me just write it down like this. Suppose you have S1, S2, S3 up to S of n as system variables. Okay. Now, this is the set S say. Now, in this set there is a small subset. So, P be a small subset of S. This subset will qualify to be a set of state variables if first of all the elements in the set are linearly independent, and if you know the information of these variables for say time t greater than equal to 0, and the input, if you know the information about these variables and the input, using these you can find out the information about the other system variables also. Okay. Then the question arises, what is that smallest set? How do I know what is that smallest set? Okay. So, that we have to find out. So, how do you say that something is, what is the smallest set among, if you are given a big set, in that big set what is the smallest set that will qualify as state variables? So, the number of elements that will be present that will qualify as state variable generally is equal to the order of the differential equation describing the system. So, if you write down a differential equation of the system, you remember, right, we wrote down this LTI systems differential equation, which was basically derivative of the outputs equal to some derivatives of the input. We wrote down a sum of derivatives on both sides. Now, the order of this differential equation, the highest degree of the differential equation, the order of the differential equation generally is the number of state variables that you need to take for a system. There is another way of finding out how many number of state variables can be there for a system. See the problem is, when you have a system, you might not know, right, which will be the state variables. First question is that. Then if how many state variables should I choose? Because system variables maybe you can easily check, okay, these are the system variables, but among those system variables you have to take a subset, right. Now, how many elements will be there in that subset, that you will have to find out, right. So, one way is that if you know the order of the differential equation of the system. Okay. The other option is that if you look at the system, find out the energy storing elements of the system. Okay. So, the number of energy storing elements in a system will give you the number of state variables. So, if there are 3 energy storing elements, then there will be 3 state variables. Okay. Now, in case if you by mistake select less than the number of energy storing elements or less than the order of the differential equation, then you will see that you will be not able to write down the differential equation for the entire system. So, whatever differential equation you will write, that will not represent the entire system. Okay. Now, let us take this example, these 2 examples that we were talking about. Now, in case of this RLC circuit, you see we directly from the circuit itself we know that inductor and these 2 capacitors are the energy storing elements. So, in this case these 3 will be, so there will be 3 number of state variables. Now, the question is which are the state variables you can choose. There are many ways of choosing state variables. One straightforward way here in case of at least RLC circuits is that what is the formula for energy? Li square, right, current through the inductor is what changes, right. So, you will take IL to be one state variable. In this case it is CV square, right, voltage across the capacitor square multiplied by C gives you an energy, right. So, voltage across the 2 capacitors will also be state variables. So, in this case the state variables in this case would be IL, VC1 and VC2. VC2 is basically the voltage across this, okay, and VC1 is basically the voltage across this. Okay. Now, in case of the mass spring damper system, you see what will be the state variables. Again, in this case, if you try to write down the differential equation will be mx double dot plus bx dot plus kx equal to f. This is the differential equation. I am not writing the time variable here, but you understand that. So, you see this is a second order differential equation. So, there will be 2 states. Now, which are the 2 states you can choose? Generally for spring mass damper systems, position and velocity we choose. Okay. So, in this case there will be 2 among the system variables, you can choose 2 state variables. So, we will choose position and velocity. So, this will not be a state variable. Okay. This has been mistakenly written. So, this is not a state variable, remember. So, there are 2 state variables in this case, this is x and x dot. Are these the only state variables? No, you see, remember if I say it in the definition, you can come up with a different state variable also. This also will become a state variable. This is also a state variable, although it does not have any physical meaning, x plus x dot and x minus x dot, because you cannot write x plus x dot in terms of x minus x dot. In similarly, you cannot write x minus x dot in terms of x plus x dot. So, they are linearly independent anyways, and we have 2 elements. So, these will also become your state variables. So, state variables are not unique, okay, but the number of state variables will be unique. So, for example, in this RLC circuit we have 3. So, you can come up with some other state variables also. We will see soon what do I mean by that. Okay. Fine. This is what state variables are. Now, this gives rise to the state vector. So, once you have the state variable, you can take the state variables and stack it up as a vector. So, for example, in the RLC circuit, we had IL, VC1 and VC2 as the state variables, right. We had 3 state variables. These were your state variables. So, in this case, this becomes your vector. So, this vector we will call a state vector. Okay. What is the look at this state vector. So, in this state vector is here each element is dependent on time. Okay. So, if I ask you what is at t equal to 0, what is the value of this vector? The value of this vector is I0, VC1 0, VC2 0, right. In the same way, I can ask you at t equal to 1, where is it? Where is the vector? It will be I1, VC1 and VC2 1. So, if you think about it, you can plot this entire thing into a 3D space, right. You can plot this entire thing in a 3D space, and in the 3D space, if I say this is a point, okay, here suppose the value is 1 2 1, if this axis is IL, this axis is VC1 and this axis is VC2, then this position is, this means at some time say t equal to 1, I am at 1 2 1, which means that IL is 1 at t equal to 1, Vc1 is 2 at t equal to 1 and Vc2 is 1 at t equal to 1. Okay. Now, this idea of representing it in this in this plot brings us to the idea of state space. Now, what is state space? The n dimensional space whose axes are the state variables is called state space. What is the meaning of that? If I go to the mass spring damper system, in this system there are two state variables x and x dot. So, you can take x to be one axis and x dot to be the other axis. So, we will have a state space of this form. So, at different times the states will have different values. So, at say at t equal to 0 the states are here. So, in that case, so this will become x 0 and x dot 0. At t equal to 1, suppose the state is here. So, this point becomes x 1 and x dot 1. Similarly, x 2 and x dot 2. So, now you see if there are other points also that I already know, I can join this and I can draw a trajectory. This is called a trajectory. Okay. So, that means the states are moving at different times, you have different values. So, I can join them together and form a trajectory. If I am at a point on the trajectory, I means at a particular time what is the value of both the variables. And you can see that this can have any value in this space, right? It can have any value in this space. So, this space of entire space we will call it to be state space, because this space we are representing one of the axis as xt and the other as x dot. Okay. Now, in case of the RLC circuit we have 3 states. So, in that case we will have a 3 dimensional space. Okay. So, this is a 3 dimensional state space. Now, you can imagine, although I took these 2 examples, if you have a system which has 100 states, then you will have a 100 dimensional state space. So, of course, that I cannot draw. I could draw only for 2 dimension and 3 dimension. So, as you increase your number of states, drawing it becomes difficult, but we will analyze it with the help of the matrices that we will get while doing state space representation. Now, a set of ordinary differential equation that describes how the state variable change over time in response to current state and forcing variable are called state equations. So, now we come to the modeling part of a system. Okay, now we know what are state vectors, what are state variables, what are state space, all these words we know. Okay. So, the first thing, like in case of modeling with external view or the transfer function modeling, what we did was, the first thing to identify was what was the output and the input, right? And then we found out the differential equation, or experimentally we came up with the transfer function of the system. In this setup, the first thing that you need to identify is that what are the states of the system. Okay. Once you have identified, see again, states are not unique. Okay. You can come up with a different state, I can come up with a different state, but the number of states will be same. You come up with 3, I will also come up with 3, but they might not be the same variables that we choose, both of us choose. Okay. So, in case of state space, your first work is find out the state variables. So, you write down the state variables and you write down the state variable as a vector, the state vector you have to write down. Now the first n number of equations. So, suppose that we have, let us say that we come up with n number of states. Okay, this is standard. Okay, standard as in generally we say that there are n number of states in a system. Okay, n is the number of states. Okay, n can be 2, n can be 3 depending on what you are doing. So, suppose you have n number of states. So, that means for each state variable you can write down one differential equation, ordinary differential equation, first order ordinary differential equation for each state. So, for each state you will be able to write down the first order differential equation in terms of the state variables and the input or the forcing variable. So, what I mean by that is, for example, this. See, I have chosen that there are n number of states. So, the state vector in this case looks like x1, x2 to xn. Okay, this is the state vector in this case. Now, each system variable, each state variable here will have one first order differential equation in terms of the other state variables and input. And what are the inputs I have chosen? I have chosen that there are m number of inputs, So, this is the input vector. Like we have state vector, the state vector was like this, where we took the state variables and wrote it down as a vector. We have input vectors where we take the input variables. How many inputs does the system have? Remember, we are no longer in CISO domain, we are talking about MIMO case. Although our results will be CISO later, but in general we will try to understand what a state space system is for MIMO also. So, we have a multi-input, multi-output setup. So, we have multiple inputs. So, if you have multiple inputs, there will be many number of inputs. So, suppose there are m number of inputs. You take each input and write it down as a vector, then that becomes your input vector. This is your input vector here. Okay. So, you can see that corresponding to each state variable, now I am writing a differential equation. So, the left hand side is ddt of x1, and these are linear combination of the state variables plus linear combination of the all the inputs. Okay. Now, of course, the linear combinations will be different for different cases. So, for each of them I can write down these equations. So, as a whole I have how many number of equations? I have n number of ODEs, n differential and ordinary differential equations corresponding to each state variable. Okay. Now, good thing about this is this entire thing can be written down nicely in a matrix form in this way. Look at this, whatever I wrote down here, I am writing down the same way. So, let us take the first equation x dots. Look at the first row here. So, this is x dot in the left hand side. On the right hand side, what will you get? A11 x1 plus A12 x2 plus dot 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 A1n xn. This is what this part is, plus B11 U1 plus B12 U2 plus dot 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 B1n UM. This is the second part, right. So, in the same way each row here correspond to the equations here. So, this is first equation. So, the first row of this is the first equation. This is the second equation. So, the second row here is the second equation. This is the mth equation. So, this is the mth equation here. Okay. And the good thing about this is also that you see, look at the matrix form now. Now, in the matrix form it looks so neat, right. Once I have said what the state vector is, the only two things that comes out is A and B. A is the matrix. What is the dimension of this matrix? How many number of rows? There are n number of differential equations. So, n number of rows. How many number of columns here? Because you see there are n number of state vectors here. So, n number of columns here. So, A here is a n cross matrix, and for this course we are only dealing with real matrices. So, R n cross n. So, what is R n cross n? What is this symbol? This symbol is the set of all n cross n. So, what is this symbol? This is the set of all n cross n matrices with real entries. Okay. So, A basically it means that you take the set of all n cross n matrices, in that n cross n matrices of real entries. Okay. A is one element. Okay. A belongs to that set. Set notation you already know, right? What is set notation? So, R n cross n means the collection of all the n cross n matrices where we have real entries. Now, this is a very big set, right? Now, A belongs to that set. So, that means A will be a matrix where the entries will be real. Similarly, let us look at the dimension of B. What is the dimension of B here? So, how many number of, first of all, how many number of rows here? N number of rows, right? Because there are n number of differential equations. And how many number of columns here? Because there are m inputs. So, there are m number of columns here. Okay. So, that means B is a R n cross m matrix. Okay. So, A was a n cross n matrix and B is a n cross m matrix. Remember these dimensions. So, once I know A and B, and of course, A and B depends on what are the state vector that you have chosen. So, first of all you decide the state vector and then you try to find out the value of A and matrix of matrix A and B. Okay. This equation is what is known as state equation, because this equation, this differential equation involves the states of the system. Okay. Similarly, let us first do this example and then check. So, for this RLC circuit, let us try to find out the state equation. So, how will the state equation look? First of all, as I said, if I have to find out the state equation, first thing is that you have to tell what the state vector is, because if you take a different state vector, your equation will look different. Okay. So, I am choosing IL, VC1 and VC2. The ordering also matters, right? So, you have to keep the ordering the same. So, IL, VC1 and VC2. If you take IL, VC1 first and IL later, then the equation orders will change. Okay. You can try that out on your own. So, if this is the state vector, Then let us try to write down the differential equation. So, what are we expecting? If this is the state vector, you see, remember what is the equation like? D dt of x equal to a of x plus b of u. If you go back, so this was your x, right? This was your x, this entire thing we are calling as x here, fine. So, d dt of the state vector must be equal to a into the state vector plus b into the input. So, here also d dt of the state vector must be equal to the A matrix, okay, and input and B matrix here. So, this is a 3 cross 3 matrix and this has to be a 3 cross 1 matrix in this case, because again while doing so you should also understand what is the input and the output. So, the input in this case is V t, okay. So, when you start modeling in this way, first of all state vector, then input and output, this also you should know, of course, okay, input and output should be known. But in the transfer function only input and output was enough, right. But here since it is internal variables also we are dealing with, so we will have to take input, output and state vectors, these are the internal variables, the state vectors are the internal variables, okay. So, I now want to find out these elements, no. So, the first thing is that when you write down the equations, how do we write down the equations for an RLC circuit? KVL, KCL, nodal analysis or mesh analysis, you will do something and then you will have to find out the equations, but the equations should be in this form, it should look like this, so that I can get them A and B matrices that we are looking for. So, let us look at the equation. So, the first equation I am applying the KVL here. So, in that case what do I get? V minus, so now you see the current through the resistor and the inductor here is IL. So, V minus IL into R1 minus L DIL dt minus, here I am saying that the voltage is VC1. Why I am saying that? Because you see I have to write down the equation in terms of VC1, VC2 and IL. So, what is VC1 and VC2 here? This is VC2, this is VC2 and this is VC1, the voltage across the capacitor, this is VC1. Okay. So, now I am trying to write everything in terms of, therefore, I am trying to write everything in terms of VIL, VC1, VC2 and V. Okay. I will try to eliminate anything else that comes here. So, you see this equation is already in terms of IL, VC1 and V. So, nothing has to be eliminated from here. I can rewrite this, I will bring to the left hand side d dt of IL. So, d dt of IL equal to minus R1 by L. So, this is the equation I get. So, the first equation I have got here, you can see that, okay, this is the first equation. Now, I have to find out the second equation. So, in the second equation what am I looking for? I am looking for d dt of Vc. So, where does d dt of capacitor voltage come? If I multiply C1 here, so d dt of Vc1 I want, right. If I multiply C1 here, so C1 d dt of Vc1 is current, right. So, that means I have to write down the current equation here, okay. So, let us try to write it down. So, you can see that C1 d dt of Vc1, this is the current flowing here, I2 is the current here and IL is the current coming in. So, the KCL at that point will give me this, okay. So, now from here again these are in terms of what we need except I2, I2 I do not need, right, because this equation does not involve I2. So, somehow I will have to get rid of I2. Can I write down I2 in terms of other state variables? Yes, because what is this is the current flowing through here, right. So, since the current is flowing through this way, so I can write Vc1 minus Vc2 by R2 is your I2. This I am replacing by this. Now, you see, now I have replaced I2 by Vc1 and Vc2. So, everything is in terms of state variables and input is not involved here. So, I can write down the second equation. So, the second equation comes out directly with this. Now, the third equation. So, the third equation involves d dt of Vc2. So, I have to, so this C2 d dt of Vc2 is current. So, the current here. So, I will have to apply KCL here. So, I am applying KCL C2 d dt of Vc2 equal to I2, because I2 is the current coming in. But again I2 can be written as Vc1 minus Vc2 by R2. So, we will have this as the expression, because I2 is coming from this direction. So, Vc1 minus Vc2 by R2 will give me the current, and this will be by expression of the third differential equation. So, what I can do is I can easily replace this by this now. See what I have done, all these equations, the coefficients I am taking the coefficient minus R1 by L, you see minus R1 by IL plus, so you can see the equations minus R1 by L IL minus 1 by L Vc1 and then 0, and then we have plus 1 by L Vt. So, this is coming. So, in the same way I have written the two equations here, and this will be your state space equation. So, this is your A matrix, this is a 3 cross 3 A matrix, and this is your B matrix when you have taken this as the state vector. So, as an exercise what you can do is you can take this as the state vector and check what will be the, if you take this as the state vector, what will be the differential equation, because all the equations are already there, you do not have to do much actually. Okay. Now, so this was what our state equation looks like. Here x of t is nothing but the collection of the state variables, and this is the state vector. Okay. So, once you know the state vector, the A and B, so the state equations are done. Now comes the output equation. So, you should know about the output. How will the output equation be written? Again, this is a MIMO system, right? So, we will have multiple outputs. So, for each output you will get one equation in terms of the state variables and the input again. Like in case of the state equation, you got differential equations ODEs in terms of the, for each state variable in terms of the state variables and the output and the input. Similarly, in case of output equation, you will get one equation each corresponding to each of the outputs. And what will be these equations like? These equations will be linear combinations of the state variables and the input. Okay. So, for example, suppose there are p number of inputs. Okay. So, if there are p number of inputs, I will get p number of outputs. So, for each input you see I am writing down a linear combination of the states plus a linear combination of the inputs. So, this again can also be written down in a matrix form, and the matrix form will look something like this. This is a similar thing we did like the in case of state equation, but only remember in the state equation it was a differential equation. In case of output equation, it is no longer a differential equation, it is a algebraic equation. There is no differential equations involved here. Okay. Now, let us look at the dimension of these matrices. Now, this matrix is called the C matrix and this matrix is called the D matrix. Okay. The output matrix and the feed forward matrix actually, and what are the dimension of this? The number of inputs in this case is p, so the number of rows here are p, and the number of columns in this case has to be n. So, this is a p cross n matrix, and here you can see the number of rows are p and the number of columns are n. So, this has to be a p cross the number of columns are m. So, this is a p cross m matrix. So, in case of this RLC circuit that we took, how will it look like then? So, in case of the RLC circuit, you will have to replace this by Cx plus again du, right, and you will find that the d term will not come up here, that is why I did not write it down here, but you will see soon. So, what was our output? What did we take as our output? The output in this case was Vc2. Okay, you could take something else also output, but here I am taking Vc2 as the output. So, if Vc2 is the output, so Yt equal to Vc2. Now, Vc2 written, see I have to write it down in terms of IL, Vc1 and Vc2. So, 0 times of IL plus 0 times of Vc1 plus 1 times of Vc2 is your output. Okay, so this becomes your C matrix. So, this is your C matrix here. So, there is no D matrix in this case. Okay. There can be examples where D matrix will show up, but in this case there are no examples. In this case there is no D matrix. Okay. So, what we have seen with this example is that how do we write down the state equations? The state equations are differential equations, ordinary differential equation corresponding to the states, and the output equations are algebraic equations in terms of the states and the inputs. Okay. Here A matrix is an n cross n matrix. These dimensions are very important. If there are n number of states, so we say that A is an n cross n square matrix. B, if there are m number of inputs, we say that n cross m. B will be n cross m. C will be p number of outputs, so p into n, and D will be a matrix p into m. Okay. Remember the dimension of the matrices. This will be very helpful for you. Okay. So, in the next lecture what we will do is we will take some more examples and try to find out state space models for those systems. Thank you.